Yeah.
It is full screen already. Okay. Yes.
Now it's okay.
Welcome, Professor Grover, Emeritus Professor HBNI, and member is Professor Pedinai, Dean HBNI, Professor Tomar, and other senior colleagues of HBNI, and all participants available on online. And Professor, I welcome you all to this DAE Iconic Week celebration of Azadi Ka Amrit Mahotsav. Today we are on the second day of this celebration, and today the topics are of mathematical sciences and chemical. As you all know that mathematics is a fundamental part of logic, and it helps us in understanding the world and our own life. Mathematics provides an effective way of mental discipline and encourages logical reasoning and mental rigor. In addition, mathematical knowledge plays a crucial role in understanding the contents of other subjects such as sciences, social sciences, and even music and art. Firstly, we ask the question, why does mathematics hold such an important and unique place among other subjects? So some of the answers are like mathematical literacy is a crucial attribute of individuals, citizens. Mathematical literacy is like we said, in various sciences, social sciences, music and arts requires mathematics. And in this particular case, number theory is very, very important. So I'm very much thankful to Professor Thangadurai our HBNI's invitation for giving iconic week celebration for Azadi Ka Amrit Mahotsav. His topic today is challenges in number theory. A brief introduction of Professor Thangadurai. Professor Thangadurai did his PhD in combinatorial number theory during 93-99. Then he did his postdoc fellowship under Professor R. Balasubramanian Kolkata in April 2003. He joined as faculty member at Harishchandra Research Institute in 2003 and present at HRI. He has written 65 research articles in internationally reputed journals in mathematics and has guided 8 PhDs. 4 of them are continuing for their PhD thesis. He has guided 4 master's students as well. Award for the year 2017 from the proceedings of Indian Academy of Sciences, Mathematical Sciences. In 2018, he became a fellow of the. I welcome you, sir. And that stage is yours, sir. Thank you.
Thank you, sir. I'm thankful to HBNA and Professor Dureja for giving me a big introduction. My topic is challenges in number theory. Just before that, I will briefly go through. One second. Yeah, briefly go through opportunities in mathematics, and then I will get into my main topic. Brief discussion on opportunities in mathematics. First topic is research and academics. Then second one is banking sector and insurance. Then third one is data science, business analytics. Then e-commerce. So first one is this is what our main thing, research and academics. So master level students after masters they get into PhD. So for that national level entrance tests, which are kind of NBHM, CSER Net, GATE, and the Indian Statistical Institute entrance test, Chennai Mathematical Institute or TIFR entrance test, followed by interviews at various institutions. So this is for PhD or integrated PhD. Even bachelor students, so one can try to write this exams. Just I am just giving a glimpse of institutions, top institutions in India. One is HBN institutions where mathematics, just I have given only 4, where I mean 3, only math research is done, and then Tata Institute and Indian Institute of Technology. I mean, there are many put together. I am just giving the icons. Okay, then ISER, there are several ISERs, and then Indian Statistical Institute, CMI, and Indian Institute of Science. Okay, these are here one can, I mean, go for PhD or integrated PhD. Under HBNI, there are 3 institutes doing, I mean, where the mathematics research is done. HRI, IMSC, and NICER. Their admission to PhD or integrated PhD program through NBHM PhD scholarship written test or CSER fellowship top rank, they will be called for for post, and then junior research officers in various central government departments, and educational officer in this is meant for all kind of science, I guess. Educational officer in Indian Army or Navy or Air Force. Okay, these are all just government departments. The next one is we are talking about where mathematics graduates or master level students can go in the private sector or industry. So banking and insurance is one such. So this is one has to kind of along with the master just usual MSc, one should have a actuarial science also, kind of which is towards finance and banking sector topics. If one has, I mean, math students are preferred just because of their ability to think logically and problem solver. Okay, so this is just I'm just giving a glimpse because my main topic is something else. So in this actuarial science in India also, Indian government established Institute of Actuaries of India in 2006. So one can one can go to this website and check out what are all careers opportunities for in this line of thought. The third one is if a mathematics student has skills in designs and analysis of algorithms and mathematical formula to study data, then one can kind of hope to get into data science and or business analytics. Okay, this kind of thing is called knowledge process outsourcing. The process of I mean, what one they do is they collect data and they have to analyze the data, and they have to kind of predict, kind of give insight to the business or the industry, whatever they are collecting data for. This kind of institutions are there in India, namely name a few: GE, Genpat, TCS, Infosys, Tiger Analytics, Play Game, etc. Okay, so here master level students and bachelor level student also one can, I mean, hope to get this kind of. The next one is e-commerce. E-commerce is, I mean, they use a lot of probability theory models and queuing theory models, non-linear dynamics, graph theory, and number theory for this cryptography side. The okay through in terms of e-commerce, the opportunities are in R&D sections of IT firms. One has to know more. I mean, other sectors possibly one has to know more of statistics and probability more. Okay, this is just a glimpse. Just other than research, also, I mean, academics also, what are all other opportunities for master level students in mathematics? Okay, so let me come to my main topic of the lecture: challenging problem in number theory. Okay, number theory as such, if one see the history, It is more than 2000-year-old subject. It has been there since Euclid time, which is he is before Christ, he was before Christ. Okay, so therefore I start with one of the oldest problems still unsolved. I start with chronologically. Everybody, it's a well-known problem, and it's a conjecture of Goldbach. Okay, Goldbach lived in 1690 to 1764. The conjecture states it's a simply number theory problems are easy to state, difficult to solve. This is one such instance. The conjecture says that any even integer greater than greater than or equal to 6 can be written as sum of two odd primes. This is very simple-minded statement, but still it is very we don't know except one remarkable result. This conjecture Goldbach stated in a letter to Euler in 1742. 1742 he wrote he wrote this problem, but 1975 Chen came up with the ingenious idea of closer to this conjecture. What he proved is every sufficiently large even integer can be written as sum of either two primes or a prime and almost prime. Means almost prime means it is not a prime, but it may be a product of two primes. Okay, so this is what the best so far known towards this conjecture. It's 300 years old problem almost. Using the method of sieve theory, Chen proved this remarkable result. Another related conjecture of Goldbach, it is related to this particular conjecture. This is called ternary Goldbach. This was proved by Vinogradov in 1937. So, which states that every sufficiently large odd integer can be written as sum of three primes. Okay, this statement he could prove for all sufficiently. How large it is, that stage that time he could not compute. Some few years back, Helfgott he could complete this stage also. That's the reason I have put his photograph here. And Atli Selberg is the inventor of sieve methods. One of the sieve method which is very useful and very powerful also. This problem is Goldbach conjecture is still open. Otherwise, other than the Chen's result, this is one of the oldest so far. The next one is Gauss primitive root conjecture. Gauss Artem. I have written. So 1800 Gauss, a German mathematician, he was trying to study the decimal expansion of some rational numbers, like which is of the form 1 by p, where p is a prime. When p is a prime not equal to 2 or 5, the decimal expansion 1 by p is purely periodic. Already it is known. So purely periodic in the sense the digits, some finite digit keep appearing. Yeah, okay, periodically. Okay, that's what purely. This is the way I have written A1, A2, AL. For instance, this is keep repeating in the after decimal expansion. Okay, decimal point. So where L is the least natural number. I could have chosen 2L also, one such. A1, A2, AL, A1, A2, AL together also it's going to repeat. So, but we choose the least one, where A's are the digits. Therefore, it lies in between 0 to 9. So what Gauss observed, once he write down 1 by p equal to this type, then he observed that since it is a decimal expansion of the 1 by p, this is base 10. So what he observed is 10 power L is congruent to 1 modulo p. It means 10 power L minus 1, the integer, is divisible by p, which means that the 10 in the group theoretic language, that the integer 10 lies inside the group, multiplicative group of z modulo pz. The order of 10 is nothing but L. So this is what first he observed, And when L equal to P minus 1, it means the cardinality of the group P minus 1. P minus 1 is nothing but the cardinality of the group. It means the 10 is a generator of this group. So he termed it as 10 as a primitive root modulo P. So whenever L is for those primes P, this L is like P minus 1. Then he called 10 is a primitive root modulo P. Okay. So then by checking, he on hand he checks many values, and he found that for many initial primes, this 10 is indeed a primitive root modulo P. Then he asked a question whether this 10 is a primitive root modulo P for infinitely many primes or not. In 1920, Emil Artem looked at Gauss' question in more generality, along with algebraic number theory input, and with his heuristic argument, he posed the following conjecture. In fact, he gave a quantitative version of this the conjecture. The Gauss-Artem conjecture, it says, let B be a non-square integer. Non-square means it's not a square of an integer, and B is not equal to 0 or plus minus 1, then there exists infinitely many primes P for which B is a primitive root modulo P. It means this given B is going to be a generator for Z modulo P Z star for infinitely many primes P. Okay, so for many years there was no progress, but assuming certain strong hypothesis, that hypothesis I will be, roughly telling that it has been proved that if one assumes that hypothesis, then this conjecture is true, kind of thing is known. But unconditionally, nothing was known until Professor Ramurthy and Gupta. They, in 1983, what they proved is any 11 non-square integers if you take, which are not equal to 0 or plus minus 1, then one of the 11 chosen integers is going to be a primitive root modulo P for infinitely many primes P. But one cannot pinpoint that which integer among the 11. So any 11 you can choose, and then among that 11, one is going to satisfy this conjecture. So in 1987, this 11 has been improved to 4 by Heath Brown, of which, yeah. So, other than these results, Gauss Artem primitive root conjecture is still an open problem, and we don't know for given one value. Not even one example we know. Among them, kind of, we cannot pinpoint this is for which this is going to be true, kind of. This is again near about 200-year-old problem. Okay. Another is, I'm just because number theory means it's about prime numbers. So because of chronology, somehow I didn't start with Euclid. Now I am starting with Euclid. Okay. Euclid proved that there exists infinitely many primes, and he proved the fundamental theorem of arithmetic, which states that every integer can be written uniquely as a product of prime powers up to its order. It means unique up to order. Okay, so since there are infinitely many primes, we enumerate these primes. First prime is 2, therefore we call it P1, and second prime is 3, we call it P2, and third prime is 5, we call it P3, etc. So yeah, Pn means nth prime. Then we look at the prime sequence Pn. By elementary arguments, one can just either Chinese remainder theorem or very elementary way, one can check that the limit supremum of this sequence, the difference Pn plus 1, the two consecutive difference Pn plus 1 minus Pn, limit supremum, this tends to infinity. It means large gap of composite numbers, consecutive composite numbers exist. This is what this particular statement says. Arbitrarily long consecutive composite numbers exist in integers. Okay, so instead of limit supremum, we ask the same question for limit infimum. Then it becomes a non-trivial question. Okay, the analogous problem. And more generally, you fix some natural number m, and you just jump gap of m gaps among the prime sequence. That means Pn plus m minus Pn. I am looking at consecutive but m gap. Okay, so this limit infimum, this itself hard. This then this is going to be much harder. Okay, so this is the question. This is a non-trivial question. This is not like lim sup? Okay, I come to 2012. Zhang proved that this limit infimum of Pn plus 1 minus Pn, the consecutive primes, the limit infimum is finite number. It means there are there are infinitely many primes. There are infinitely many primes P such that P and some finite gap you can kind of get it. For instance, if you take 3 and 5, the gap is 2. 5 and 7 gap is 2. 7 and 11 gap is 4, kind of. So, but this says that there exists a finite number such that there exist infinitely many primes P such that P and P plus some A, where A is less than or equal to this bound. There are infinitely many such primes exist. In 2015, James Maynard, he proved for any given m the general problem. Here since m is there, it is consecutive primes. Here we are jumping with m gap. Therefore, this finite bound should be as a function of little whatever given input m. Okay, these questions are coming from where? The general conjecture. These questions are coming from the prime k-tuple conjecture, which was first. I mean, the previous slide. Dixon. He gave this conjecture for this conjecture is kind of Dixon conjecture, but Hardy and Littlewood gave a quantitative version of this conjecture. So generally, it is called prime k-tuple conjecture. So what it says, it talks about the position of primes. These are all hard problems, position of primes. What it says in general, suppose you are given A1, A2, AK, natural numbers. It can be integers, but I am assuming here natural numbers. K number of natural numbers are given, such that only one condition it should be satisfying. It is an admissible set. Admissible set. Okay, for the time you assume it is like 0, 2 or 0, 2, 6, this kind of admissible set. Okay, so if you fix any admissible set, if you fix for any given k, then there are infinitely many natural numbers n such that you translate this set by that natural number n. You will get all those are prime numbers. A1 plus n, A2 plus n, etc. AK plus n, all are prime numbers. Okay, this talks about prime positions. Okay, so if we start with the admissible set, then there are infinitely many translates contains only primes. Okay, this is what prime k-tuple. So these two problems, what they, I mean, Zhang and Maynard's approach is to provide a positive answer in some sense to this kind of question, this prime k-tuple conjecture using C methods in analytic number theory. But problem, this prime k-tuple conjecture is completely open, not a single case it is known. What? Because, okay, this limit infimum, Pn plus 1 minus Pn, that expected answer is supposed to be 2, because we can see that 3 and 5, 5 and 7, 7 and 11, 11 and 13, and then 17 and 19. These are all primes with the gap 2. The expectation is that there are infinitely many primes P such that P and P plus 2 are primes. Both are primes. So that if that happens, then this is limit infimum is going to be 2. But this finite number is not close to 2, little away from 2. Okay. This is another general theorem, general conjecture in analytic number theory. Okay. Now, I want to get into there are, in number theory, we see that analytic number theory, algebraic number theory, transcendental number theory, and arithmetic. Because this kind of name comes because number theory is full of problems, and whatever tools we use, accordingly, this gets the name. The problems are classified into analytic or algebraic or transcendence kind of. So this last two questions are coming from analytic side. The next question is going to come from algebra side. Okay, algebra little bit theory oriented. So let me try to give a glimpse of it. Let F be a field and K be a field over F. It's an extension field, a finite extension, field extension over F. So the Galois, this Galois was trying to solve a open problem in 1800, which was, so any that time main open problem was degree, any polynomial of degree greater than or equal to 5, it is known to be, it's not, there exists a polynomial of degree n where n is greater than or equal to 5. Okay, so this cannot be solved like the one we can solve for the lower degree polynomials, radicals we call it. Okay, so the roots cannot be given a kind of roots of it, we cannot give a formula for kind of. Then Abel proved that this kind of existence he proved for all degree greater than or equal to 5. There exists a polynomial for which we cannot give a kind of formula. Galois, during that time, what he did was he was trying to classify. These are all just, I am putting it very roughly, trying to classify all those polynomials for which we can find the roots kind of for using formula. Okay, so for that what he did was he proved a fundamental theorem which is the origin of many problem in algebraic number theory. This fundamental theorem, what it says, if K is a kind of Galois extension over the field F, here Galois extension means if one root is there, all the roots are there. Okay, underlying a polynomial. So if K is a Galois extension over a field F, then there is a one-to-one correspondence between the intermediate fields of K and F and the subgroups of the Galois group. Here Galois extension means there is an automorphism. He attached a group to this particular field extension. If it is a Galois extension, then he attached a group which is an automorphism group of K over F, which is, we call it a Galois group. And if one can study the subgroup, that corresponds to the studying the intermediate fields of this K over F, and vice versa. Moreover, in this correspondence, if there are normal subgroups, okay, then normal subgroups of this Galois group corresponds to the Galois extension, the intermediate field, whether it is Galois or not. Okay, this correspondence is both ways, one-to-one correspondence. Okay, so the Galois classified all the intermediate fields of a given Galois extension K over F. In the above problem, K over F is a fixed Galois extension, and the classification of Galois sub-extensions of K over F was answered satisfactorily. Suppose if we fix the base field F and without taking the super field, which is Galois extension, without fixing, First, we fix only the base field F and ask the similar classification as follows. What is the classification? Classification problem is describe all the finite Galois extensions over F. This is one of the, just a basic and fundamental problem. Okay, how long, how far we have gone in this problem? Okay, Galois himself answered the above question completely when the base field F is a finite field with Q elements. Q is like a prime power, any prime power. In fact, he proved that any finite extension of F, the finite field, is a Galois extension and its Galois group is cyclic. Okay, so after that, Kronecker and Weber, what they proved, if K is a Galois extension over Q, Q is the field of rational numbers, and its Galois group, K over Q, is abelian. If it is abelian Galois group, then K is contained in NS cyclotonic field. Okay, so this is generated by just roots of unity attached with nth roots of unity attached with rational field. By many mathematicians' ingenious work, now it is known by class field theory that if F over Q is a finite extension, field extension, then there is a one-to-one correspondence between all the Galois extensions K over F, whose Galois group is abelian, and the set of congruent subgroups of modulus M, which depends only on the field F, what underlying field F. So this is like just like a Galois fundamental theorem of Galois theory. This is the work of many mathematicians. In fact, this took almost 1 century to come up to this level. Okay, therefore the problem 4, describing all the finite extensions over F, is a kind of wide open, even when where F is a finite extension of Q, and whose Galois group is non-abelian. This is indeed a very challenging and fundamental problem to tackle in number theory. This is an algebraic side. Now, one problem in arithmetic side I want to kind of state. Algebraic geometry is a study of solution sets of polynomial equations. So we take polynomial equations simultaneously, where it vanishes, you look at all the solutions together. These sets are called algebraic varieties. The major, classification problem is classify all the algebraic varieties. A special case of algebraic variety is a solution set of one polynomial equation. There it can be general algebraic variety can have many polynomial equations. Here one polynomial equation, which draw more attention in the history. This kind of varieties are called curves. This is a variety of dimension 1. Okay, curves C, we denote it by C. So this is a technical assumption which says this kind of set we don't want to consider those sets which can be decomposed into union of two such similar sets. Okay, so this is kind of smooth and absolutely irreducible. We assume that. Okay, so these curves are classified according to their genus. This is coming from topological notion. This genus G. Okay, so some given a kind of number attached to this curve. When G is 0, this curve is called a line or cone. If C is if C is a cone, we understand the line when it has a kind of solution. What are the points satisfying the line? If it is a cone, then it is known that that set, algebraic set, whatever the solution set, is either empty or infinite. Okay, in fact, when it is non-empty, for that there is a clear cut kind of condition, which is we call it a local global principle by Artem. That Artem, what they proved, if C is this is the underlying two variable polynomial, but one equation which is you look at all those. This is the curve. Suppose if it is a cone defined over Q. Defined over Q means the coefficients of the polynomial coming from this particular field. Then the algebraic set, whatever the solution set, is non-empty if and only if this solution set, by considering it as real solutions, that should be non-empty. And so from Q we can get R by completing, by looking at, in rational numbers, there are gaps. By filling up the gaps, we can get the real number. Similarly, this filling up gaps is the notion is coming from a distance. We can define, there are more, given a prime number, we can define some distances, distance metric. Those distances, when you kind of complete through that distances, then we get kind of, for a given prime P, we get QP. This is a field. This is a field containing Q. This is a R. R is a real number, a field of real numbers. This also containing Q. Okay. So this curve, we can think of it is sitting defined over R and defined over QP for every prime P. Whenever this over defined over R is non-empty, or whenever this QP over QP is non-empty for every prime P, then this is kind of if and only if. Okay, one might think that this is kind of infinite condition. This is a finite condition. Only one field only we have to consider. But somehow this over R and QP, we can able to tackle this solution set easier than this over Q. Okay, so this QP denotes the field of periodic numbers. This we call it a local. Since local solution can be checked relatively easier, it's not trivial. It's relatively easier. Therefore, this answers problem 5 for genus 0 curves. When G is greater than 1, the genus is more than 1. In 1983, Faltings proved that the solution set is a finite set for any curve of genus bigger than 1. Okay, what is remaining is genus equal to 1. The curve C of genus 1 is called elliptic curve. This is a kind of two. If I draw the picture of this elliptic curve, okay. So first C can be defined as the solution set of y square equal to x cube plus a x square plus b x plus c, where the coefficients a, b, c are coming from the underlying field K. Okay, so we can have a kind of over real. We can able to write. We can kind of draw the curve. Okay. Oh, sorry. Okay. So in this, when the curve of genus 1, the local global principle fails. Therefore, there is no satisfactory answer to predict when elliptic curves have non-empty rational points on them. So in that sense, problem 5 is more general. Classify all the algebraic varieties, even variety of dimension 1. This is not completely solved yet. Okay, John Coates, Andrew Wiles, Joseph Hastarle, their contribution to elliptic curves is more, so I just picked up. Okay, so I hope. Okay, so I will come back to some elementary nature. Statements. This is the final little. Technical side. This is the modern goal of number theory. Therefore, it is important to kind of state here. Suppose if I collect all the algebraic numbers. Algebraic numbers are those numbers, complex numbers, which are roots of a polynomial with integer coefficients. That algebraic numbers I collect and put it in Q bar. It's a set of all. Q bar is a set of all algebraic numbers. It's a field of algebraic numbers. we call it algebraic closure of Q. This is a infinite Galois extension. This is a huge field. Its Galois group we denote it by GQ, Galois group of Q bar over Q. This is we call it absolute Galois group, and this group is a topological group. This is the inverse limit of all finite Galois groups. Okay, the problem, this is the modern goal. The problem 6, this is the study of the absolute Galois group as a topological group and its Galois representations. This is the modern goal of number theory. So already we have seen the Kronecker-Weber theorem. Let me recall. Okay, so Kronecker-Weber theorem, what it says, if K is a Galois extension over Q, then and the Galois group is abelian, then that K, that field is contained in a cyclotomic field, nth cyclotomic field. That statement we can rewrite it in terms of this way. The maximal abelian extensions over Q is denoted by Q of mu infinity, because I said that cyclotomic extensions are generated by root of unity. So we take the complete union of Q of zeta n, where zeta n is the nth primitive root of unity. Okay, then the Galois group we denote it by GQ abelian. Okay, this is the maximal abelian Galois group over Q. This is kind of Kronecker-Weber. Okay, so we are getting into deep water. I am going to be very sketchy for just next 2 slides. After that, statements will be easier to understand. So let G be a group. B is a vector space over a field. A representation rho of G is a group homomorphism from G to GLV. GLV is a matrices, okay, over V. This is equivalent to an action of group G on V, in the sense that if we take group element G and vector space elements V1 and V2, if G dot V1 plus V2 is nothing but G dot V1 plus G dot V2, it's a group homomorphism. That kind of whatever group operation is preserved in this map. When F is a complex numbers, field of complex numbers, GL1 of C is C star. C star is nothing but non-zero complex numbers. This is a multiplicative group of non-zero complex numbers. Then the Kronecker-Weber, in this language, Kronecker-Weber theorem, which says that any representation rho from the absolute Galois group to C star factors through the maximal abelian Galois group over Q. That means, so we want to understand the absolute Galois group. So we want to understand all the representations. So first thing is that one has to understand the characters of this particular group. This characters of this group is kind of correspondence with the characters of this maximal abelian extension, abelian group. Okay, GQ abelian. This is what Kronecker-Weber says. Okay, we are going towards one major problem given by Langlands, which is for that I am just proceeding. It is known that this absolute Galois group is a not solvable group. This, since it's an inverse limit of finite Galois groups, and the inverse Galois problem, which is not solved completely. What is the inverse Galois problem is, which asks whether all finite groups arise as a continuous quotient of this absolute Galois group or not. Okay, since it is not completely solved, this is GQ is very difficult to study. 1970, Shafrevich solved the inverse Galois problem for all solvable groups, which puts the kind of another approach. Since Q is a subfield of the periodic field QP for any prime P, one can embed this algebraic closure of Q into the algebraic closure of QP, the field QP, because Q is contained in QP, algebraic closure also contained in QP bar. So we can embed the local Galois group. I mean the Galois group of QP bar over QP. Okay, the local Galois group GQP into absolute Galois group GQ. So this local Galois group is solvable group. Therefore, one can one can kind of hope to study. Actually, what we have seen is we have seen the characters of GQ, the absolute Galois group, and we want to extend the characters to, instead of GL1, we want to get a homomorphism from GQ to GLN K for some field K. Okay, so for that, this is one way to approach this problem, is construct since GQP is a solvable group, one can kind of hope to construct representations from this solvable group to GLNK and patch it up together to get some information about this row. Okay, this patch it up together is completely, I am putting many things under carpet. Okay, this compatibility conditions. Okay, this is called, okay, this is, we roughly put it in this words. So kind of GL1 object is kind of characters. We kind of n-dimensional generalization of this Dirichlet characters, we consider that the compatibility conditions for varying primes is called kind of automorphic forms. These are the kind of stalwarts in this automorphic side of Galois representations. J.P. Sayre, Richard Taylor and Harris, and Peter Solje. Okay, so let me just these three slides are the real technical slide. The final modern goal is Langland's program. Is Robert Langland's. The what he proposed is the correspondence between the Galois side and the automorphic side. This is like the Kronecker-Weber theorem said that the characters of GQ, the absolute Galois group, is kind of correspondence with the characters of the maximal Galois group. Okay, so likewise, it's a generalization of that. This is completely open. It's very, I mean, this is what many will be trying to solve this. This is a modern approach of number theory. Let me come back to the, okay. So this Langland's program, though it is like algebraic oriented, where the analytic side, this is going to give information about the analytic side also. So for that, we start with Raymond hypothesis. Okay, Raymond, among the various important contribution to analysis and geometry, his contribution to number theory was a tip of an iceberg, which is called Raymond hypothesis. It's a still open problem, not only for his Zeta functions, but also for many natural generalization as well. Okay, let me just introduce Zeta function. So for a complex number, yes, Raymond Zeta function is defined as the series summation 1 by n power s. The Raymond proved that as analytic Zeta s is an analytic function for all real part of s bigger than 1 and has a simple pole at s equal to 1 with residue 1. He also proved functional equation for Zeta s and extended using that he extended Zeta s meromorphically to entire complex plane with only one pole at s equal to 1. Okay. So using the functional equation, he observed that Zeta s as a 0 when s equal to minus 2n, where n is a natural number. Yeah, all negative even integers, this is vanishing. And he conjectured that in this strip, I mean, real part of s is in between 0 and 1. Okay, the Zeta s, if it vanishes,
Alert him, I think he's mute.
Hello, sir.
Here things are fine only. I don't know.
Yes, now fine.
Yes, sir. Now we can hear.
Now you can. Okay, let me share. It's visible, right? Yeah. Okay. It's not full screen, but it's visible. Maybe I'll just continue. Uh, okay. So how many minutes I have? Okay. Okay. Yeah. Fine. So the Langlands program kind of gives a light on this L series in the analytic side. What this kind of series, so what it says, it suggests a higher moments of this L series and their arithmetic nature, which connects that to in the side of automorphic side. Okay. Oh, this is a problem. I have to be in full screen. Is it audible now? Hello?
Yes.
Yeah. Okay. So this okay. I will just quickly go. So Erdos conjecture. This is combinatorial side, combinatorial number theory. So if we partition the natural numbers into finitely many parts, then one of the part contains arithmetic progression of arbitrary length. This is what Van der Waals proved in 1930. In 1975, Zemredy, he using ingenious combinatorial argument, what he proved is if a subset of a natural number is big enough in the sense of upper natural density is positive, then it contains arbitrary long arithmetic progression. Arbitrary long means not infinite. Given any k, I can find an arithmetic progression of length k. That's what it means. Okay, later Furstenberg proved Zemredy's theorem using ergodic methods, and in 1998, Timothy Gauss improved the quantitative version of Zemredy's results. Okay, where is Erdos conjecture comes in this setup? This was a question of Erdos, and he conjectured the following more general. The big so suppose of course that time it was understood that a subset has upper natural density positive, then it is huge, it is big enough. Then Erdos conjectured that it is not only just upper natural density positive, but if you take a sequence A1 less than strictly, I mean the A1, A2, AN, it's a subset of natural numbers such that the reciprocal sum is infinite, then also it should be kind of large enough. It means if it is large enough, then the sequence should contain arbitrarily long arithmetic progressions. This is the conjecture of Erdos. When AN, if we take AN to be Pn, Pn is the nth prime in the above conjecture, summation 1 by Pn tends to infinity. I mean, this sum is infinite. So when AN equal to Pn, therefore it was expected that this prime sequence should satisfy this conjecture. But however, computationally it was really impossible, infeasible. Why? Because that time it was known only up to 24 length arithmetic progression among primes, and that two largest known primes had to be used that time. In 2000, Terence Stowe and Ben Green, they proved this conjecture when AN is Pn, the prime sequences. So other than the prime sequences, this Erdos conjecture is completely unsolved. This is a very natural Borel's conjecture. It's a 100 years old problem in number theory. This is about decimal expansion of a real number. We just stick to 0, 1 interval. Any real number inside 0, 1. it means the decimal expansion will look like 0.A1, A2, A3, etc. So what Borel conjecture deals with, all kinds of pattern should exist in the digits. That's what he deals. So in fact, is stronger conjecture is that kind of conjecture is that I am just quickly going roughly telling that what is this conjecture. So one can define a frequency. Suppose you fix a pattern in the sense the block of digit. You this b equal to 10. If you take, suppose I fix a 0, 0,
Which company
0.
you are telling?
Hello.
Which company? कौन सा company बोल रहा है आप?
Okay. Hello. Yeah. So the given block b of length k occurs with the right frequency. The frequency means how many times this block b appearing in the digits. Okay, block appearing in the digit. That is measured by this kind of limit. Okay, so a real number is said to be normal to the base b for each k, for every integer k greater than or equal to 1, every block of length k occurs with a frequency 1 by b power k. So the 1 by b power k is the maximum number of different blocks. Okay, that this is the right frequency in some sense for occurring a block of length k. Okay, so 1900, what Emil Borel proved, almost all real numbers are normal to the base b for every b greater than or equal to 2, and he conjectured that every algebraic irrational must be normal. Okay, so algebraic irrational, if we take square root 2, for instance, square root 2 is an algebraic irrational number. This if you write it in terms of digits, that digits in the decimal expansion, all patterns should occur. Unfortunately, we don't know even every digit occurs in square root 2. If we take b equal to 2, of course we know 0 and 1 occurs, but otherwise it is not known at all. So not even one length 1 we know, and the conjecture is meant for any length, any block of length k. So important progress was made by Mahler and then Adamski and Bujo Luca. Okay, so then how much time I have? I'm kind of okay. So this is about transcendental number theory. Just I wanted to give the glimpse of all type of number theory. The first transcendental number means which is not algebraic number. So first transcendental number was example was given by Liouville in 1844. That number is the series type. This sum of 1 by 10 power n factorial. This number is a real number, and it is a transcendental number. Later, E and pi were proved to be transcendental. Cantor proved that the set of all real numbers are uncountable. Okay, the set of all real numbers is uncountable. Therefore, and the set of all algebraic numbers is countable. Therefore, almost all real numbers are transcendental. Okay, so he proved the kind of existence. I mean, almost all real numbers are transcendental, but the techniques are not enough to understand this bigger set of real numbers. Okay, so I'm just okay. So there are conjectures. This is the kind of last. There are three conjectures, major conjectures in transcendental number theory. One is Shanwell conjecture. Another is Zeta values, Raymond Zeta function at 2n plus 1. I mean odd Zeta values, and Baker's conjecture. Okay, so I am not getting into. This is my last slide almost. So far, I mean, after Ramanujan, of course, Indian number theories means Ramanujan comes into picture, and Ramanujan's time and after, there are many contributors. Though I have not kind of stated, you may think because I didn't take the line of thought of this mathematician's contribution that way. That's the reason I was checking only fundamental problems so far, whatever left. Okay, so these are the mathematicians in Ramanujan's time and after. They worked in number theory. I mean, these are all my mentors in number theory. They helped in many ways for my number theory knowledge. I just wanted to give a gratitude by doing this. And my contemporary number theorists, Eknath, Ramana, Ravi, Shauli, Purushottam, Anandavardhanan, Anirban, and my HRI number theory colleagues, Aprameyo, Dalawat, Gyan, and Chakravarti. Then personal admiration coming from all this Indian contribution. With that, I thank you for your attention. I'm really thankful to many internet resources for various mathematician photographs and materials for this presentation. Thank you.
Thank you so much, sir, for a detailed information on number theory.
Hello, sir.
Do you have any question, please?
Yeah.
The hall or somebody? If anybody has a question on online mode,
Hello.
thank you so much. On behalf of everyone, thank you so much, sir.
Thank you, sir.
Thank you.
Okay, sir.
What like it?
So, on behalf. So, on behalf. Thank you. Or other lecture. Thank you, sir. Thank you.